So here there's a few more terminologies that we are going to be talking about. So let's look at it this way. We start off with a bunch of vectors, v1 to vn here, all these yellow guy. And we like to find if I can multiply v1 by something, v2 by something, and so on to vn by something. So my x here, these are my variables, so they are scalar. And my v, the yellow guy, these are my vectors. We like to see if what are the solutions to this when my right hand side is just the zero vector. Now we can see for sure that this equation definitely has one solution. I can simply let all the x be 0. So if all these guys are 0, then my left hand side are going to be 0, and that is going to be a solution for sure. Now then, if the zero solution is the only solution, then I'm going to say that the vectors v1 to vn. So we knew, so let me just write on the side here. We knew upon seeing this that 0, 0, 0, 0. This is a solution for sure. This is a solution. But now the question is, well, are there any more? Are there more solutions than that? If there is more solutions, so there are solutions to this guy other than 0, 0, 0, 0, then we're going to say that my vectors of v1 to vn here are linearly dependent. But if the zero vector is the only solution, then we're going to say that these guys are linearly independent. So the opposite of dependent is just independent. So let's just take a look at my example down here. I'd like to see if these vectors are linearly dependent or independent. So basically what I'm going to do is I'm going to solve this equation. So I'd like to see if I can find x, y, and z such that x times the first guy plus y times the second guy and z times the last guy. I'd like to find what are the solutions to this vector equation. So my right hand side is going to be just 0, 0, 0. So then we knew that, well, I can just let my x and y and z be 0, and that would be a solution for sure. But now the question is, well, are there more? Can we find solutions other than 0, 0, 0? So let's try to solve this guy. Now, if I were to write this in matrix form, I'm going to get 1, 2, 9, 5, 1, 3, and then 11, 4, 15. And my right hand side would just be 0. Now, this should look strikingly familiar, but let me just solve this just like we normally would. So if I do the row operation on this guy, I can divide the third row by 3. So I'm gonna get, let me see, 1, 5, 11, 2, 1, 4, and then 3, 1, 5. So let me just do this very quickly. Then I can subtract 2 times row 1 from row 2 and then 3 times row 1 from row 3. So I'm gonna get, let me see, 1, 5, 11, and then 0, negative 9, negative 18, and then 0, negative 14, negative 28, and then my right hand side would just remain 0. Now then I can divide the second row and the third row by negative 9 and negative 14 respectively, and I'm gonna get 0, 1, 2 here and 0, 1, 2 here. Now I'm going to subtract 5 times row 2 from row 1 and subtract just the row 2 from row 3. And I'm gonna get 1, 0, 1, and then 0, 1, 2, and then 0, 0, 0 here. And my right hand side would just be 0. Notice how, well, because my right hand side starts off with being 0, so no matter what I do, it will just remain all 0. Now then, if I were to convert this back into equation form, into system of linear equation form, I'm gonna get x plus 0y plus 2z equals to 0. So that means x plus c equals to 0. And then my, let's see, y plus 2z is gonna equal to 0. And my last equation would just be 0, equal to 0. So I can just ignore that. Now then, if we look at this system of equation, notice that I actually have a free variable, my variable c here. This is my free variable. So that means I can let this c be anything. So my solution would just be, I can let the value c be anything, and then my x would just be negative c, and my y would just be negative 2c. So what that means is, there are definitely many solutions to this equation. So I can let my c be anything, and that would be a solution to this guy. For example, if my c is 0, I would just get 0, 0, 0. If my c is 1, I'm gonna get, let's see, negative 1, negative 2, and 1. If my c, let's say, if my c is negative 3, I'm gonna get 3, 6, and negative 3. So all these guys are gonna be the solution to this vector equation that I have. So that means there are solutions other than 0, 0, 0. And when there are more solutions other than 0, 0, 0, that means I'm going to be in the first case now. So that means these three guys are linearly dependent. So these three guys are linearly dependent. Now let's take a look at the next one. Once again, I'd like to determine if these three guys are linearly dependent or independent. So what I'm going to try to solve is, I can find x, y, and z, so I'm just going to play sheet and just copy my previous equation. And ta-da! So I'd like to see if I can find x, y, and z such that my x times 129 plus y times 513 plus z times negative 3, 5, 6 is equal to 0, 0, 0. So once again, I can turn this into the matrix form. That would just be 129, 513, negative 3, 5, 6, and then 0, 0, 0. Now let me actually just go ahead and write the reduced row echelon form for this guy. I'm gonna get 1, 0, 0, 0, 1, 0, and 0, 0, 1 here. So if I go back and rewrite this as an as a linear equation form, I'm gonna get x equal to 0, y equal to 0, and z equal to 0. So that means the only solution to this equation, the only solution to this vector equation is just 0, 0, 0. Is the only solution. And when 0, 0, 0 is the only solution, that means I'm gonna be in the latter case now. So that means the vectors here are linearly independent. So these three guys are linearly independent. And as you may have guessed, this is actually not a coincidence because if we look at all the yellow guys, okay, so if we take a look at all the yellow guys V1 to Vn here, if any one of them is a linear combination of the other guys, then that means all the yellow guys are gonna be linearly dependent. So if we look at part A here, we have seen that the last guy here, 11, 4, 15, this is actually a linear combination of the other two. So from the last bullet here, whenever one of them is a linear combination of the rest, that means they are linearly dependent. So that's kind of what we see here, because the last guy here, this is a linear combination of the other two, so they are linearly dependent. But for the latter part, none of them is a linear combination of the other two. For example, if I were to do this, then the vector negative 3, 5, 6, this is not a linear combination of the other two. And the same remains true no matter how I pick the other two vectors. So for example, the 5, 1, 3, this is not a linear combination of the other two. The 5, 1, 3, this is not a linear combination of 1, 2, 9 and negative 3, 5, 6. So this is what it means for vectors to be linearly dependent and linearly independent. I'm gonna talk about how this concept plays a role in the other part of mathematics in the next example. But for now, let me just give you a quick overview of what this actually kind of really means. So this is just a metaphor, by the way. So imagine we are making Coca-Cola for sale. So I'm gonna have a Coke. So I'm gonna have Coke and Coke Zero, for example. And then Coke Zero. Okay, so this is kind of what we have here. Now, let's say one day I introduce a new product and I'm gonna call that product. Okay, so let me try to do this. So let's say one day we introduce a new product and I call that, let me see. One day we introduce a new product and I call that Coke 0.5. So what happens is I'm just gonna put half a Coke and half a Diet Coke, half a Coke Zero all together in a can. And I call that Coke 0.5. Then this guy, well, is just a linear combination of the two. Combination. So what really happens is if I'm a consumer, then I can just walk in and see that, oh, you are actually not adding a new product. This is just a linear combination of the other two products that already exist. So this is not really interesting. This is nothing new to the market. I can just buy one can of this and one can of this and mix it at home myself. So this is nothing new to the business. And if I were to add this three together, that will make them linearly dependent. So these three guys are linearly dependent. So you can kind of see that the Coke 0.5 here is a redundant product. I don't really need them. I can only just sell Coke and Coke Zero and that would be fine. Now, in the other scenario, let's imagine if I have Coke and Coke Zero and one day I introduce a new product and I call that Sprite. And it's totally different from Coke and Coke Zero, so this guy is now not a linear combination. Not a linear combination. So it would seem as if I really add something new to the market, and if I put these three together in a set, they are gonna be linearly independent. Okay, so these three guys are gonna be linearly independent. So you can kind of compare this to the other scenario where I'm just playing cheap and just add like half a Coke and half a Coke Zero and call it a new product. So